Super oscillations are fascinating wave phenomena where a wave oscillates faster than its highest Fourier component, enabling the imaging and manipulation of objects smaller than the wave's wavelength. Traditionally, the diffraction limit in optics and wave physics restricts the resolution of imaging systems, making it impossible to observe features smaller than half the wavelength of light. However, super oscillations break this limit by creating regions of highly concentrated energy through precise interference patterns. For example, carefully engineered light waves can form super oscillatory hotspots, allowing scientists to image nanoscale structures or manipulate single molecules with light that traditionally couldn't resolve such tiny details. Imagine trying to paint fine details on a canvas with a broad brush, but discovering a way to control the bristles so precisely that you can create intricate designs. Super oscillations hold immense potential for advancing microscopy, nanofabrication, and even quantum computing, as they provide tools to probe and manipulate matter on unprecedented scales.
Super oscillations are wave phenomena where a signal or wave oscillates at a frequency higher than its highest Fourier component. This defies conventional understanding of wave physics, where the Fourier transform defines a signal's frequency limits. Super oscillations arise from the interference of multiple wave components, resulting in regions of high-frequency oscillation interspersed with broader, lower-frequency patterns. Example: a carefully designed optical wavefront can exhibit super-oscillatory regions, where the light oscillates with a spatial frequency finer than its wavelength. Analogy: super oscillations are like using a coarse net to catch fine particles. Though it seems impossible, careful arrangement allows fine details to emerge within a larger framework. In classical optics, the diffraction limit imposes a restriction on the resolution of imaging systems, defined as approximately half the wavelength of the light used. Super oscillations challenge this by creating localized regions of high-frequency oscillations, enabling sub-diffraction imaging and manipulation. These hotspots allow researchers to observe and interact with features smaller than the wavelength, breaking free from the constraints of traditional wave physics. Example: super oscillatory light patterns have been used to achieve nanometer-scale resolution in microscopy, enabling the visualization of structures far below the diffraction limit of light. Analogy: breaking the diffraction limit with super oscillations is like photographing intricate details of a distant object with a camera lens previously thought too coarse to resolve such precision. Super oscillations result from constructive and destructive interference of wave components in a carefully engineered waveform. By precisely adjusting the amplitudes and phases of these components, regions of oscillation faster than the wave's highest Fourier component can be created. These regions are surrounded by areas of destructive interference, often referred to as side lobes, which balance the wave's overall energy. Example: analogy: super oscillations are like choreographing a dance, where individual movements create fleeting patterns of incredible speed and precision within an otherwise slow performance. Super oscillations are a powerful tool in super-resolution microscopy, a field that seeks to surpass the diffraction limit of light to achieve nanoscale imaging. By forming super-oscillatory light patterns, researchers can create fine focal points that enable imaging of structures smaller than half the wavelength of the light used. Unlike conventional super-resolution techniques that rely on fluorescent markers, super oscillations can be applied to label-free imaging. Example: super-oscillatory optical systems have been used to image biological samples at resolutions previously achievable only with electron microscopy. Analogy: using super oscillations in microscopy is like viewing the fine print of a document with a magnifying glass that can resolve details smaller than its lens allows. The concentrated energy of super oscillatory hotspots can be harnessed for manipulating nanoscale objects, such as molecules or nanoparticles. By creating precise light distributions, super oscillations enable optical tweezing, nanolithography, and single-molecule spectroscopy, where targeted interaction with specific nanoscale features is critical. Example, superoscillatory fields have been used to trap and move nanoparticles with unprecedented spatial precision, facilitating advancements in nanofabrication. Analogy, nanoscale manipulation with superoscillatory fields is like using a laser pointer to write fine calligraphy on a grain of rice. Superoscillations play a role in quantum technologies by enabling precise control of quantum systems and enhancing sensitivity in quantum measurements. In quantum computing, superoscillatory fields can be used to address individual qubits or manipulate quantum states with high spatial and temporal precision. Additionally, superoscillations can enhance imaging techniques used in quantum sensors. Example, tailored superoscillatory patterns have been proposed to manipulate trapped ions in quantum computing architectures, improving scalability and precision. Analogy, superoscillations in quantum technologies are like using a scalpel instead of a hammer to carve intricate structures in fragile materials. Despite their promise, superoscillations come with inherent challenges. The regions of high-frequency oscillation are typically surrounded by large side lobes, areas of destructive interference that limit overall energy efficiency and practical implementation. Additionally, the precision required to generate superoscillations demands advanced wavefront engineering and computational modeling. Generating superoscillatory light fields often involves trade-offs between hotspot intensity and the suppression of side lobes, requiring careful optimization in experimental setups. Designing superoscillatory patterns is like building a sandcastle on a beach. Achieving intricate details is possible, but requires constant adjustment to prevent collapse. Superoscillations challenge conventional interpretations of wave physics, particularly regarding the relationship between a wave's Fourier components and its spatial resolution. They provide a framework for understanding how information and energy can be localized beyond traditional limits, contributing to broader advancements in optical science and wave theory. Research on superoscillations has uncovered new ways to design waveforms for applications ranging from telecommunications to acoustic imaging. Superoscillations offer new insights into waves, akin to discovering hidden shortcuts in a map that allow travel to previously unreachable destinations. The ability to engineer superoscillatory patterns opens new frontiers in nanoscale imaging, nanofabrication, and light-matter interaction. Future advancements could enable compact, high-resolution imaging systems, breakthroughs in molecular manipulation, and innovations in quantum technologies. Superoscillatory lenses are being developed for portable, high-resolution imaging systems with potential uses in healthcare, material science, and beyond. The revolutionary potential of superoscillations is like discovering a new art form that allows painting on canvases invisible to the naked eye, unlocking previously unimaginable creative possibilities.